Hi, this is Professor Fernandez, and this is video 1 in lesson 13. We're talking here about the concept of linearization. So before I go ahead and do this example from Calculus Simplified that gets us comfortable with the mathematics of linearization, let me just review very quickly the concept behind linearization. So I'm going to just draw you a function here, f of x in blue, right? And we already know that if we zoom in a little bit here, if I pick an a value, x equals a over here, right? Then if I draw the line that's tangent to this a value, there we go, this tangent line. If I zoom in a little bit, right, so if I keep zooming in, this is a little blurry on the screen, but you can notice that over this small interval, this line, this tangent line, is a pretty good approximation to the blue curve, the function, right? And we'll see that throughout this example that I'm going to work out with you in a little bit. So the idea is that, if you have the function curving and you have the tangent line, right, near the point x equals a, then the tangent line is a very, very good approximation to the function when you zoom in through a very, very small window. So why is that useful? Well, so we haven't made too much use of this in this course so far. We've just focused on, interpreting the tangent line, on calculating the slope of the tangent line. That's the derivative f prime of a. We focused on, in the previous videos, finding derivative rules for calculating that derivative as a function, for example. But this is the video where we start thinking about this really interesting notion. Again, that if you zoom in, and the more you zoom in, close to the point a, f of a, the tangent line looks more and more like the graph. Or put the other way, the graph looks more and more like its tangent line. So if we were to try to write this out in a very preliminary formula, we would say that f of x is approximately, let's just call the tangent line L of x, L for line, is approximately L of x for x near a. Right? That would be one way to phrase it. In other words, the values of the function f of x are approximately the values of the tangent line when x is near a. And then you might wonder, okay, what is the equation of this tangent line? Then you would say, well, it's a line, so it's y equals mx plus b in the simplest form, that is tangent to the graph at the point a comma f of a. So it's a comma f of a, okay? And it's a tangent line, so it has slope f prime of a. So if we use these two pieces of information, we could use the point slope equation. We end up with an equation for L of x that is f prime of a times x minus a plus f of a. So that is L of x. The equation of the line that's tangent to f, the graph, at point a comma f of a, at x equals a. Okay, so if we put this together with that, then I'm going to scroll down here to the definition of linearization. There it is, right? F of x approximately equal to its tangent line. Its tangent line we've been calling, again, L of x. So when you read through this definition, right, either you're doing it now, I'll zoom in so you can see the whole definition, or you're doing it through your reading of Calculus Simplified, have that picture in mind that I just drew over here, right? And I talk about this in the book as well. Fundamentally, what you're doing when you're approaching this linearization concept is you're taking the function f of x, whatever values it has, near x equals a, and you're approximating it by the tangent line values for x near a. Okay, and again, we'll see this very clearly in a minute when we work through this example. Okay, so I'm going to zoom out here, and that is the end of my little quick intro / review of this linearization concept. Let's actually apply it here to this example. So we're going to calculate the linearization of square root of x at x equals a, or sorry, at a equals 1. So again, the linearization down here is the actual equation of the tangent line. It's just got a different name. You might wonder, why a new concept? Why not just say calculate the equation of the tangent line? We could, but here we're using the tangent line for other purposes, right? For the purpose of approximating the values of the function and linearizing the function. So we call it the linearization. Okay, so what do we need? We're calculating this down here. We need the a value, a equals 1. We also need f of a and f prime of a. Great. So f of a, in this case, a equals 1, so it's f of 1. And the function is square root of x, so square root of 1, that's 1. Great. We need f prime of a, so we're going to need to differentiate the function. Square root of x is x to the 1/2. Power function, so power rule for its derivative. There we go. And then substitute in 1, that's our a value. 1/2 times 1 to the negative 1/2, that's just 1/2. So now we have the f of a, we have the f prime of a. So this implies that the linearization is L of x down here, right? So that's f of a, which is 1, plus f prime of a, which is 1/2, times x minus a, which is 1. Great. So I could simplify this, and we might as well do that just to see a little more cleanly what it's going to turn out to be. So it's 1/2, and this is a negative 1/2 plus a 1, so that, 1/2 x. Negative 1/2 plus a 1 gives us plus 1/2. Factor out the 1/2, and I get x plus 1. Great, so I'm going to scroll over here and write down our conclusion, which is that f of x, stemming from this notion that we just reviewed. So this conclusion for this particular example turns into this very nice statement, that the square root of x is approximately 1/2 times x plus 1 for x near x equals 1. Okay, so this is a really cool thing, right? Especially, if we're doing this back in the day when calculus was first being developed. Square root of x, these days you can use a calculator, you can use your phone, you can go online, and you can calculate square root of, 37, right? You approximate it very quickly. Back in the day, we had no way of doing this. We didn't have the technology. So in a sense, calculus was the technology that allowed us to do this. It said if I want to calculate square root of 37, then first of all, I should figure out an a value that I know the square root of x for. So square root of 36, that's 6. Great, and then I could run through the exact same process that I just did with a equals 36 and find the approximate linear function, right? The linear is crucial here, because then I could just find wherever the x value is and plug in 37, and I would get an approximation for square root of 37. Because 37, that would be the x value, would in that case be near the a value, 36. So that's how you would actually use this if you were wanting to approximate values. We'll do that in this example in a minute. But first, let me just finish the stated question here. Plot your result along with f of x over these intervals, and then comment on what you notice. So that's what I did down here. These three graphs are actually figure 4.4 from Calculus Simplified. And what's happening here? So the function here, f of x, is in black. So let me change that to black. And then the graph that the linearization resulted in, which is the linear function 1/2 x plus 1, is graphed in blue. So you can see what's happening here, right? This is what I mentioned earlier in this video about zooming in. So if I look at this first graph, notice what the window is. X goes from 0 to 2, and then y goes from 0 to 1.41. Which is about, square root of 2. So if I look over here at what's happening, the point of tangency is a equals 1, right? And f of a, which is f of 1, square root of 1, also 1. So the point of tangency is the point 1, comma 1. So there we go. And you can see that the graph of the linearization, right, the tangent line, is pretty close to the graph of the function, right? So this tangent line here looks very close to the graph of the function, which is square root of x. If I now zoom in and zoom in more, right? Look at the window here. Now it's 0.5 to 1.5. Smaller or narrower range than what I had before. Then look what happens. This graph, right on this graph, if I look at the point 1, comma 1, the function and its tangent line there start looking more and more like each other. And then if I zoom in even more, right, a very narrow window for the x values around point 1, comma 1, I have like almost indistinguishable graphs between the tangent line and its original function square root of x there. So for example, if I wanted to approximate square root of 1.05, all right, then the y value would be the value on the graph of square root of x, which is the black almost line looking here. But because of this nice calculus concept of linearization, what I could do then is I could just use the value on the tangent line when x is 1.05 to actually approximate square root of 1.05. So to use the equation we just calculated up here, that would tell me square root of 1.05 is approximately 1/2 times 1.05 plus 1. And then I would just work this out. This is 2.05 divided by 2, which is 1.025. And this ends up being very, very close to the actual value of square root of 1.05, which is 1.0247 dot dot dot. Very close approximation, right, to the actual value of square root of 1.05. We'll talk more about that in a next video, but I'll zoom out here and just do a quick little review. So we talked about the fact that linearization is nothing other than an attempt to use the fact that the tangent line to a graph at a point, when you zoom in, looks very, very much like the graph itself, right? So have this picture down here in mind. So, written out mathematically, that means that the values of the function are approximately equal to the values of the tangent line when the x value is near a, the point of tangency. And then if you kind of develop this, you unwrap it like we did in the beginning of the video, that gives you an actual equation for the tangent line, and then that gives you a way to write down those approximations. So last quick little thing I'll mention, there is a distinction, and I put this down here in the definition, between finding the linearization and finding the linear approximation. Very subtle distinction, but the distinction is there. The linearization really is just, again, another word for the equation of the tangent line. The linear approximation is when you're actually trying to approximate a function using that tangent line, right? So that's more like what we were doing down here, which is in fact a preview of what we'll do in the next video. So hope to see you there.